Okay, let's say we have a container here, schematic. We have a container here. Of a container of water at a temperature of 77 degrees C and a pressure, let's see here, what's my pressure? Pressure of 100 bar. Pressure equals 100 bar. So given H2O at a temperature of 77 degrees C and a pressure of 100 bar. 1 atmosphere is about 1 bar. Remember, a bar is a 10 to the 5th Pascal. So 1 bar is an atmosphere approximately. 1.01 bar is an atmosphere. So this is about 100 atmospheres. It's a lot. Very high pressure. Okay? So we have H2O, 77 degrees C, and at a pressure of 100 bar. What are we supposed to find? Oh, how much H2O do we have? We have 2 kilograms of the stuff. So mass is equal to 2 kilograms. Okay, what are we supposed to find? Let's find the volume of the H2O, the internal energy of the H2O, and the enthalpy of the H2O. Let's find these 3 properties of the H2O, okay? Okay, so first of all, let's figure out where we are, what the state is. Let's figure out what the state is. Always a good idea, necessary to figure out what the state is so we can figure out what tables to use or how to approximate quantities. So, analysis. So here is our TV plot. Let's just do the TV plot. So here's our dome. Okay, there's our dome right there. And let me put in the 100 bar isobar. 100 bar, okay? 100 bar isobar. Now, let's look up the saturation temperature, the boiling temperature for H2O at 100 atmospheres, or 100 bar, approximately 100 atmospheres. Let's see if we can find a Tsat here. Let's see here, share. There we go. So let's look at pressure tables. Here we go, 100 bar, 311.1 degrees C. That's the boiling temperature at 100 atmospheres or 100 bar. So Tsat at 100 bar is 311 degrees C. So let me turn this off. 311 degrees C, that's Tsat. So here's 311, Tsat 311 degrees C, okay? Now we're all the way down here at 77 degrees C, okay? So this is our state. Right there. We're at 100 bar. We're on that isobar somewhere. We're on this isobar somewhere. And we're at 77 degrees C. So T is less than Tsat. So this implies super cooled liquid. Okay, so that's our state, supercooled liquid, supercooled liquid. Okay, let's proceed. Let's proceed here. I want to find the I want to find the volume of my container of H2O, supercooled liquid H2O. So volume will be equal to the mass of the H2O times the specific volume of a supercooled liquid evaluated at 77 degrees and 100 bar, okay? If I know the specific volume for my supercooled liquid, multiply it by the mass, then I will get the volume of the liquid. Now let's use our approximation here. So this is approximately equal to, looking back at R, and I've condensed the approximations up here. Specific volume for a supercooled liquid at any temperature and pressure is approximately equal to that for the saturated liquid at the temperature. So this is approximately equal to the mass times the specific volume of the saturated liquid at T equals 77 degrees C. Okay? Okay? Now let's see if we can find in a temperature table 77 degrees C. Let's see what we can find in our temperature tables. Okay, that's pressure table, temperature table, saturation temperature tables. I do not have 77 degrees. I've got 70 and I've got 80. That means we're going to interpolate between these two. Here's our specific volume for the saturated liquid at 70 and 80. So specific volume is going to be somewhere close to 1.027. So there's 0.022. 0.027, we're closer to 80 degrees than 70 degrees. So 1.027 times 10 to the minus 3 cubic meters per kilogram is probably the approximate specific volume. Let's get the exact interpolated specific volume by using some kind of linear interpolation. Let's linearly interpolate between these 2 points. Let me show you how this is going to work. So specific volume, here's temperature, here's specific volume. As temperature goes up, liquids expand. So there's some kind of a relationship like that between specific volume and temperature. Now let's put a couple of data points in. Our tables give specific volume at 70 degrees and 80 degrees. In fact, let's look those up again. Let's see here, 70 degrees, 1.0228, 1.0228, 10 to the minus 3. We put the unit in here, cubic meters per kilogram. And then at 80 degrees, it is 1.029. 1.029, 10 to the minus 3. Okay, 1.029. Forget the 1, okay? So those are our relevant quantities. Whoops. Okay, so 70 and 80 degrees, we have specific volume at 70 and at 80. And as specific volume goes up, when temperature goes up, okay, there's some sort of relationship between specific volume and temperature. Now we want specific volume at 77 degrees C, okay, 77. We want to know what this is. Specific volume of the saturated liquid at 77 degrees C, okay? We want to know what that is. Now, what we're going to do is we're going to put a linear connecting line between these 2 points. Assume this is a straight line. And we're going to calculate the specific volume based on that straight line interpolation. So how's this going to work? Specific volume for the saturated liquid at 77 degrees C, approximately equal to, I'm going to take this as my origin for my interpolation. So V sat liquid at 70 degrees C. So this is where I'm going to start. And then I'm going to move from this point out here. Okay? So V sat liquid plus delta specific volume over delta T. So that's the slope of this straight line, times 77 degrees minus 70. The rise over the run on the chart and how far we're moving away from our origin data point. 77 minus 70 degrees, okay? Now, what's the delta V over delta T? Let's see, delta V over delta T. That's going to be equal to specific volume, and I'm not going to write sat liquid, I'm just going to write liquid at 80 degrees C minus specific volume of the saturated liquid at 70 degrees C. The rise, okay, the rise and the run is 80 degrees C minus 70 degrees C, okay? Now let's see if I got some numbers here for you. Let's see here. We have, so 1.0291 minus 1.0228. So this is I guess I'll put the numbers in here. 1.029, I'll leave the 1 out. 10 to the minus 3 minus 1.0228. 10 to the minus 3. And that'll, of course, all have units of cubic meters per kilogram. Don't have enough room for the unit there. And then I have 10 degrees C. Okay, so delta T down below. Let's see here, 1.029 minus 1.0228 divide by 10, and there's a 10 to the minus 3 in there. Okay, and we get something quite small here. So this is, oops, I gotta make sure this is right. 1.029 minus 1.0228. And then we divide that by 10. Okay, so I get 6 times 10 to the 1, 2, 3, 4. So that's 10 to the negative 7. 6.2, 10 to the negative 7. And that is cubic meters per kilogram per degree centigrade. Okay, that's what the slope is. So V sat liquid at 70 degrees, 1.0228, 10 to the minus 3 kilograms per cubic meter, plus the slope, 6.2. I'm going to take out the 10 to the minus 3 there so everything's in the same unit. 6.2, 10 to the negative 4. The 7 becomes a negative 4 cubic meters, kilogram. And then I have my delta T. This is going to be 7 degrees C. Oops, cubic meter per kilogram degree centigrade. Cubic meter per kilogram degree centigrade, and then I have 7 degrees C. We crank that all out and we get 1.027. 1.0272 10 to the minus 3 cubic meters per kilogram. Okay? So that is the interpolated, linearly interpolated specific volume at 77 degrees C. 1.0272. Let us plug that in and get our volume. Let's see here, the mass was 2 kilograms and 1.0272, 10 to the minus 3 cubic meters per kilogram. The kilograms cancel out and I get cubic meters. Okay? Kilograms cancel out, so I get cubic meters, which is what I want, and I end up with a final volume of 2.054 cubic meters. So volume of my supercooled liquid at the temperature and pressure is 2.054 cubic meters. So let's put a box around it, okay? 2 cubic meters. Oh, sorry. I was like, God, that's huge. 10 to the minus 3. 10 to the minus 3. Don't lose it. That's much better. 10 to the minus 3. This is about 10 to the minus 3 cubic meters is a liter, so this is about 2 liters or half a gallon. That's much better. So volume, 2.054, 10 to the minus 3 cubic meters, or if you like, 2.054 liters. And there's about 4.25 liters in a gallon. So that's about half a gallon or so. Okay? All right. Let's calculate internal energy. Let's calculate internal energy. U. Let's move over here now. U at the temperature and pressure. Well, U, let's see, so that's going to be the mass of the H2O times the specific internal energy of the supercooled liquid. Evaluated at 77 degrees C and a pressure of 100 bar, okay? And that's approximately equal to, using the approximation, the mass of the H2O times U of the saturated liquid evaluated at 77 degrees C, okay? So there's the approximation right there. Now, if we go through the same process, instead of having specific volume here, I linearly interpolate for internal energy. So let's go to the tables here. So specific volume, specific internal energy of the saturated liquid. So now I can interpolate between these two specific internal energies. Looks to me like we're going to be about, so 77 degrees is closer to 80. So just eyeballing it, it looks to me like we're going to have like 320 or 325 kilojoules per kilogram, just eyeballing it. So we can do the same interpolation. We can do the same interpolation that we did for specific volume. Same exact kind of interpolation. And I can get U for the saturated liquid at 77 degrees. Okay, so kind of running out of space here. So let's see here. If you do the interpolation, you'll find that this is 300 and 22.29 kilojoules per kilogram. And this is from interpolation. Interpolation, okay? Using the tables. Using the tables. Okay, so I got 2 kilograms of this stuff. 322.29 kilojoule per kilogram. And I end up with 644.6 kilojoules. Running out of space. U equals 644.6 kilojoules, okay? And we're interpolating internal energy instead of specific volume, okay? The procedure is exactly the same. Take the specific volume at 80 degrees and 70 degrees, internal energy at 70 and 80, and interpolate between those 2 data points, okay? Using a linear interpolation. So that's U. What about H? What about H? Well, we're going to need the specific enthalpy of the supercooled liquid, so we can use this equation here. It's approximately equal to that of the saturated liquid plus pressure times the specific volume of the saturated liquid. So let's use that approximation to estimate the enthalpy of our supercooled liquid. So H equals mass times the specific enthalpy. And again, this is a supercooled liquid. At some temperature and pressure, and that's approximately equal to, well, I'll tell you what, let's just leave it at that. I'll plug it in just a minute. Let's see here, H of a supercooled liquid. At some temperature and pressure, approximately equal to U of the saturated liquid at the temperature T, plus pressure times specific volume of the saturated liquid at temperature T. So there we're using our approximation. Now we got most of this stuff. Let's see here. U of the saturated liquid, specific internal energy of the saturated liquid. Getting a little sloppy here. Specific internal energy of the saturated liquid. So this guy is U sat liquid at 77 degrees C, okay? From interpolation, 322.29 kilojoules per kilogram. 322.29 kilojoules per kilogram, so that's the first term there. Pressure is 100 bar. Okay, 100 bar. And then specific volume of the saturated liquid, 2.0, I'm sorry, did I erase it? I guess it's right here, 1.0272. 1.0272, 10 to the minus 3 cubic meters per kilogram. Okay? Now we got some unit stuff to work on here. This is kilojoules per kilogram, and I got bar, meter cubed per kilogram in this term. I need to convert this into kilojoules. Let's see here. So a joule is a what? A Newton per meter squared. A Newton per meter squared. And a Newton, well, so let's convert out a bar first. So let's see here. Let me convert this into pascals. There are 10 to the 5th Pascal per bar. The bars cancel out right now. There we go. So now we got Pascal meter cubed per kilogram. So a Pascal, we want kilojoules. So a joule is a force, a Newton, over a meter. That gives you a joule, a Newton over a meter. A Pascal is a Newton per meter squared. Okay, that's a Pascal. So that means this whole term here, meter cubed will partially cancel with the meter squared, and I'll have Newton meter per kilogram. So this will cancel with all but one of the meters there. I get a Newton meter per kilogram. Now I need to convert this, and this is a joule. That's a joule per kilogram. Newton meter, joule per kilogram. Okay, I need to convert that into kilojoules. So there is 1 kilojoule per 1,000 joules. And so this will cancel with this, and I'll end up with kilojoules per kilogram. 322.29 kilojoules per kilogram. And then I've got all this stuff. Let's see here. A lot of numbers there. A lot of numbers. Let's see here. Oh boy. Well, I got 100. So 1.0272. So I got 10 to the 2, 10 to the negative 1, 10 to the 4th. Okay? And then now I'm down to 10 to the 1st power. So this is 10 to the 1 kilojoules per kilogram. So I get 10.027 kilojoules per kilogram, and that gives me a final specific enthalpy of 332. I don't think I've rounded here, 0.6. 0.6. That looks about right. Kilojoule per kilogram. So that's the specific enthalpy of the supercooled liquid at the temperature and pressure. 2 kilograms, 332 kilojoule per kilogram, and I end up with H of 665. 665 kilojoules. So note the kilograms cancel out. So 365 kilojoules. H equals 665 kilojoules. Okay? All right. Okay, so that's it. We got U, H, and volume.